Hi, and welcome to the third lesson in higher physics, motion time graphs. This is really the first part of motion time graphs because today our learning intention is going to be looking at a revision of National 5 motion time graphs and velocity. We've got a little bit to do further than this, but if you understand the basics, then hopefully the rest of it will fall into place quite easily. So the success criteria today, broadly speaking, we need to know that the area under velocity time graphs equals the displacement. The gradient of a VT graph gives you the acceleration, and we want to understand a little bit about how positive and negative velocity affects velocity time graphs. So we're going to start off by looking at a basic VT graph here. Speed time graph, as we would call it probably at National 5, I quite often interchange the words speed and velocity, but in reality at higher we're really looking at it in terms of velocity, but we'll come back to that concept later on. It's a good idea whenever you're drawing these kind of graphs to put in units afterwards, even if you don't need units. If you get into the habit of doing this, then it means that when you do need units, they'll be there anyway, and put a 0 in the corner. And the first thing we're going to do is I'm going to show you a very quick example of a motion time graph that you might have got at National 5. So there's one there. Now hopefully you remember that's an acceleration. Now up here, and I know I've gone a bit beyond the graph, but if I put in the number 10, put 4 there, I'll put another 0 along the bottom as well. We don't need to do this, but just to make it clear, this is 0 for time as well, and 5 seconds here. So what we've got is effectively a 5-second journey where some object is moving, accelerating from 4 meters per second to 10 meters per second. Now there's two things we can do with this motion time graph. The first thing we can do is we can get the acceleration. Now the acceleration from a velocity time graph, and this is something you really need to understand at this stage because this is something you will almost certainly need to know about. The acceleration is actually the gradient of the graph. Now, as it happens, we tend to use the equation a equals v minus u over t. And that's, if you haven't worked this out yet, that's actually a rearranged version of this equation, which we were doing last time in the equations of motion. The acceleration here is the gradient of this graph. Because it's a positive gradient, we're going to get a positive acceleration. But we'll come back to that afterwards. Let's see if we can just calculate the acceleration from the numbers we've got there. The v is the final velocity. So when we do this here, the v is the final velocity, and for this journey, the final velocity is going to be 10 meters per second. Minus u is the initial velocity, which is in this case 4. And the time, well, you've got to be careful with this in some examples. The time is always the time for the velocity to change. It's the time for the acceleration to happen. So the time at the bottom here is going to be 5 seconds. This is a simpler example, but if we had something that went along first of all and then actually accelerated, then we'd only use the time that it took to accelerate. In this case, the acceleration is 6 divided by 5, which is 1.2 meters per second. And remember, because of acceleration, it's a minus 2. It's meters per second squared. Okay, so that's basically how we calculate the acceleration from a speed time graph here. We could do it in terms of the gradient as well. This is effectively your y2. You're taking away y1, and you're taking it, this bottom line can actually be changed to 5 minus 0. So if you remember in maths, the gradient is actually given by y2 minus y1 over x2 minus x1. And that gives us the acceleration. The second thing we can do from this graph is we can actually split it up. Or we can work out the area under the graph. Now why do we want to do that? Well, the area under the graph gives us distance travelled, or the displacement. Now generally at higher, we're talking about velocity time graphs. So we're looking at the displacement. So displacement is the area under the graph. Now we have to be a wee bit careful about that word under, and I'll come back to that afterwards. But the displacement is the area under the graph. Normally you're going to have a shape that's very hard to calculate the area, so you have to divide it up into easier shapes. So in this case we're going to divide it up into a triangle and a rectangle, and I'll call this rectangle area 1 and the triangle area 2. The displacement here would be given by area 1 plus area 2. Now if you're not sure about this and can't really remember, then please go back to your National 5 notes. Area 1 here is going to be, because it's a rectangle, it's 5 along the way and 4 up the way. So it's 4 times 5. And area 2 is a triangle. So it's going to be half times the base, which is 5, times the height of the triangle. Remember, we're only looking at this height in here. So this will be 6 from here to here. So times 6. If we multiply them out, do the sums, it's 20 plus a half of 5 times 6. Well, 5 6 is 30, half of that is 15, and that equals 35 meters. Okay, if you're interested, the reason it's meters and not meter squared is because the units here are in seconds, and the units here are meters per second. So it's like meters divided by seconds. So seconds times meters divided by seconds, the seconds and divided by seconds cancel out, and you end up with meters left at the end. Okay, so that's basically our displacement. And that's what you should have done at National 5. Now the second bit of this is actually something you also might have covered at National 5. It is part of the National 5 course, but it's not emphasised very much, because at National 5 you don't tend to be asked very many questions about it. What we're going to look at is we're going to look at a graph like this again. Now this is very definitely a velocity time graph. And the reason it's a velocity time graph and not a speed time graph is because it has a negative values on this axis. Speed can never be negative. It's a scalar quantity. It just can't be negative. Whereas velocity can be. It can be positive and negative. And you should remember from the lesson on equations of motion, the difference between a positive and a negative value for velocity or displacement or anything like that is to do with direction. So basically, positive and negative are to do with directions. You can't say that positive is always up or positive is always down. It doesn't really work in that way. You can decide at the beginning of a question which is which, and if you're given a graph or if you're given some information, then you have to work out sometimes which one is positive, which one is up, and which is down. In this case, I'm going to show you a graph like this here. I'm not going to tell you what it's for. That's something you can maybe have a think about before next time, and it'll be brought up in next time's lesson. But what we're going to do here is we're going to say that up this bit here, anything that's positive is going to be upwards, and anything downwards is going to be negative. So what's actually happening here? Well, it's an object that is moving. It's moving upwards at some speed. Let's just say, put numbers on to make it easier, maybe 6 meters per second. Oops, I forgot my meters per second here, and my seconds here, and my zero. But it's maybe starting off at 6 meters per second upwards, and then it's slowing down. And as it slows down, it eventually gets to zero. So for an instant there, it's actually stopped. And then it starts speeding up on the way down. Now this is the last time, hopefully, probably won't be because I won't remember, that I use the word slowing down and speeding up. We've got to be very careful about this, because actually the acceleration here is constant. The acceleration here is constant because the gradient is constant. And I think if you can take one thing from this lesson, it's that the gradient of this graph, and we will come back to this, it will tell you the acceleration. But that's actually something that's very, very useful to know. The gradient of a VT graph. So really all we want to cover here is the concept of velocity and the concept of acceleration. So velocity and acceleration, if it's a positive velocity, then it must mean it's moving upwards. So everything in this bit from here to here, this is moving upwards. everything from here to here is moving downwards. It might not seem it from this graph, but that's actually what's happening here. Okay. The other and last thing that I wanted to point out here is that you can still use the equations A equals V minus U over T to calculate acceleration. And you can still use the concept of the area under the graph giving you the displacement, and it must be displacement here because we have a velocity time graph and we've got positives and negatives. You can still use these to calculate in the same way. The only difference here is that for the acceleration, we're going to have some negative values. For instance, in this bit down here, we'd have a negative value. Let's say this is -6. And let's say I was trying to calculate over 12 seconds, I was trying to calculate the acceleration of this entire journey. I would do A equals, and we have -6 minus, and this is 6 up here, 6, divided by the total time to accelerate there. Now I know this is, maybe at National 5 we talked about deceleration. For various reasons at higher, I don't want you to do that. I want you to talk about a negative acceleration rather than a deceleration. So that would be -12 on top, 12 on the bottom, and we get an acceleration of -1 meter per second squared. Why is it minus? It's not because it's a deceleration, because deceleration is a very strange word. Actually, although it's slowing down here, it's actually speeding up here. The speed is reducing and the speed is increasing. What does deceleration mean? In truth, it doesn't mean anything. So really at higher, we're talking about the fact that the gradient here is negative, so this is going to be a negative acceleration. The negative acceleration means that it must be accelerating downwards. This negative here, we go back and we check, and we realize that it must mean downwards. You can also calculate the area under this graph. The area under this graph will involve this area here, and this is why the word under is a little bit difficult. That's why I put it in parentheses up here, because it's not really under the graph at this side, because actually you could argue it's above. It's really between the graph and the axis. This area here is going to be a negative area. This is going to be a positive area. So the two areas under the graph would be area 1 plus area 2. So area 1 plus area 2. Now there's different ways this is done by different teachers. Some people say you take away area 2. Some people say that you make this area negative, but I'm going to do it this way. So area 1 is half times base times height. So in this case, it would be half times, I have to put a 6 in the middle. So half times 6 times 6, which equals 18. Area 2 here is going to be a half times 6 times -6. So that ends up being -18. And that gives us a very strange result that the displacement is actually 0. What does this mean? Well, if you're throwing something up in the air and then it comes back down the way, then it's going to start, it might finish, in this case certainly, it finishes at exactly the same place. This is actually a graph, and then we'll come on to this later. This is a graph for a ball being thrown up in the air and coming right back down to someone's hand. So the displacement, which is between the beginning and the end of the journey, is 0. So the maths here actually tells us what's going on. And that's a good thing about higher. Sometimes it's very hard to actually guess what's going on, but the maths here should tell you. I'm sorry if you didn't get that at the bottom here. The displacement here is 0. Right. I'd like to leave this lesson at this. We'll go on and we'll have a look at some more different aspects of motion time graphs in the next lesson or two.